Now let's see what is a convex cone. Before defining convex cone, let's see what is a cone, a general cone. Let's set C is a cone if for all x element of C belonging to C and some scaling constant alpha which is non-negative, alpha x should belongs to the set C. So let's see some examples. Here I'm drawing a cone. Okay, so this is a cone. So all the region, for example here, so this shaded region forms a cone. This extends up to infinity. Okay, so why this is a cone? Because if you take any any vector x, for example, this is an x, and alpha x, it can be this, or it can be this if alpha is less than 1, right? And another vector here, and alpha x is here. So all such scaled, non-negative scaled versions of alpha are contained within the sector. For example, here I take y, and this could be an alpha y. So this is a cone. Another example, let's consider this cone. Okay, so as of now, let's take this part, this shader region as a cone. Okay, of course this is also a cone, this part is also a cone, but let's consider cone here. So why this is a cone? If you take any vector x, then alpha x is also part of this set, right? So you are taking a vector y here, then alpha y is also part of this cone. Now my question is, if this cone and this cone convex, so by just looking at this cone, we can say that this is not a convex, right? The convex cone or convex set, right? Why? Because if you take any 2 points, for example, you are taking a point here and a point here. So what is a line joining these 2 points? It is this guy, right? So this portion is not within the set. So this is not a convex. This is not convex. What about this guy? Again, the same logic. If you take 2 points here and draw a line between those points, and this region over here is not the part of the set. So this is again not a not a convex set, right? Or not a convex cone. Now let's think how to make this convex, or how to define a convex set. Yeah, so the definition for a convex cone is, it's a cone again, and or we can say that a set that contains all the conic combination of points in the set. Here, for example, we know what is a conic combination. We already saw what is a conic combination. It is a combination like this, where the weights are non-negative. All right. So then what happens? Here we have a we have a convex cone, this region, this set. Why this is a convex cone? Because if you take any 2 points, x1 and x2, and take a conic combination, this is x1 and x2, and the conic combination, we saw what is the shape of a conic combination. It has a shape of a cone, right? So the conic combination should be within this set, right? So if you go to our previous example, let's if you cut one part of this, if you consider only one part of it, that's a convex cone. So here this guy is a convex cone. Here, interestingly, this part also forms a cone, right? So that is a convex cone. This is a convex cone. Why? Because if you take any 2 points here and joins and consider the line segment between those 2 points, that is a part of the set. Here also, if you take any 2 points and consider the line segment between those 2 points, that's the part of the set. So this is convex. Okay, so again, you may ask, okay, we have the definition of a convex cone. Let's consider, let's call this as set C. So why do you, or cone C, why do you call this as a convex cone? Okay, why cone C is convex? So we can easily verify that from this definition. So we say that if you take any 2 points and take the conic combination, that has to be within this cone, right? So then what is our definition of convexity? For all theta belongs to 0, 1, the convex combination theta x1 plus 1 minus theta x2 should belong to the same set C, right? If this is the set C, then if you pick any 2 points and the convex combination has to be within the set C. So here, if you consider a theta between 0 and 1, okay, so what you can say, that is of course satisfying this condition, which is this is greater than or equal to 0, right? In this case, what will be 1 minus theta? That also has to be, if theta is between 0 and 1, then 1 minus theta is also between 0 and 1, right? Which is again a positive or non-negative quantity, right? So when you put this constraint of conic combination, already the convexity, the criteria for convexity is satisfied. So we can say that cone C is a convex set, or it's a convex cone. So such cones are called convex cones. So the moral is, or conclusion is that all the cones are not convex, but the cones defined in this way, where we say that it is a set which contain all the conic combination of points in the set, and that sort of cones are convex. Next, we will see what is hyperplanes and half space. Yeah, so hyperplane is a set of the form X such that A transpose X equal to B. So what does that mean? We already know the equations of plane from our high school, right? So we have a plane here, and which is defined by a normal to the plane. Okay, so we say that this plane here, this guy is normal or perpendicular to this vector A, right? So A is called normal normal vector of the plane, and we also have B. So A and B together define a unique plane, right? So when we vary B, what happens? If you vary B, we will get a different plane with the same slope with a different shift. Okay, if P is equal to 0, then we have plane passing through origin, right? So let's take this plane and take 2 points x1, x1 here, x2 here, right? So these are two vectors in this plane, in this hyperplane. And so then what can we write? We know that then from the definition of the plane, a transpose x1 equal to b, a transpose x2 equal to b. Then if you subtract this equation, we can write a transpose x1 minus x2 equal to 0. What does that mean? So we have a line here, x1 minus x2, this line. So what is this statement saying? Here we say that any line in the plane is perpendicular to the normal, right? So this is expected since the plane itself is normal to this guy, right? So then if you take any lines in the plane, then that is perpendicular to the normal vector, right? So this plane is called a hyperplane. Why? Because plane can be in two-dimensional, or this plane can live in any higher dimension. For example, we have a 10-dimensional space, and then we can define a plane there. So then this is called hyperplane. Okay, so this is the definition of a hyperplane. Now we see that hyperplanes are affine and convex. Why? Because it's very easy to see. Let's take a hyperplane C. So how do you define? It is X such that A transpose X equal to B, right? Of course, A should not be 0. Yeah. So let's take 2 points, x1 which belongs to C and x2 which belongs to C. Okay, this implies A transpose x1 equal to B and A transpose x2 equal to B, right? Then let's take a third point y, which is theta x1 plus 1 minus theta x2. Okay, now if you now we want to check whether this guy is this point y is in set C. So it is easy to check. We just verify that A transpose theta x1 plus 1 minus theta x2, right? So this will be theta into A transpose x1 plus 1 minus theta into A transpose x2, which we can easily verify theta into B plus 1 minus theta into again B, which is equal to B, right? Yeah, so here for any value of theta, this is satisfied. So we can say that even if the theta belongs to 0, 1, this is satisfied, or if theta doesn't, so this is the definition of convexity, right? If theta belongs to 0, 1 and theta arcs, the weights are arcs to 1, then it is convex. But for you can very easily verify that for affine combination also this is satisfying. So there is no constraints like theta should belong to 0 or 1. So then we can say that hyperplanes are affine and convex, right? So because this proof is general for both affine set and convex sets. Yeah, so hyperplanes are both affine and convex. Now we see what is a half space. So it is the definition is something similar. half space is also of the form is set x such that A transpose x is less than or equal to b. Previously we had this is equal to b, right? So this is, sorry, this is a hyperplane where we say that A transpose x equal to b. Now we are saying that it's not a plane, it is one side, the entire space covered, entire space that lies at one side of the plane. So we say here that this region A transpose x equal to less than A transpose x less than b is the hyperplane. Okay. So now we see that, sorry, I'm sorry, A transpose x less than b, this region is the half space. Okay. So this line is the hyperplane and this region is the half space here. Now, so we saw that hyperplanes are affine and convex, but half spaces are convex. They are not affine. How do we prove this? Again, we follow a similar argument. So consider a hyperplane, or here we are proving half space. Consider half space x such that A transpose x is less than or equal to b, right? Yeah. So here you can say that. Yeah. Let's take two vector x1 belongs to C, x2 belongs to C. So for half space, what does this means? A transpose x is x1 is less than or equal to b1. A transpose x2 is less than or equal to b, right? Sorry, yeah, A transpose x1 less than b, A transpose x2 less than b. Now we take a third element, y equal to theta x1 plus 1 minus theta x2. Okay, let's see what happens if we take a combination of this. So now we want to know whether this guy is in the set C. So that here the point is that depends on the value of theta. Why? Because we can say that, yeah, we'll just see what is this. A transpose into theta x1 plus 1 minus theta x2, right? So what can we write? This is equal to A transpose. This is equal to theta into A transpose x1 plus 1 minus theta into A transpose x2, right? So now we will see whether we can plug in these inequalities here. So let's let's assume that theta belongs to 0, 1 interval. Okay. In this case, we can say that theta is positive. Oh, sorry, non-negative, and 1 minus theta is also non-negative, right? So if this is satisfied, if theta belongs to 0, 1, then both theta and 1 minus theta are positive, non-negative. In that case, we can apply this, plug in this inequality here. So then we can write that this is less than or equal to theta b, less than or equal to theta b plus 1 minus theta into b, which is equal to b. Okay. So then we put here that A transpose y, the third point, y is less than or equal to b. Okay. So that means y belongs to C. So remember here this we were able to plug in this inequality only because theta is between 0 and 1. If theta is any general quantity, like for the thetas in affine combination, this will not be valid. So this proof is valid, only valid when theta is in the interval 0, 1. So that means this proof is only valid for convex combination, right? So that's why we are saying that half spaces are convex, but not affine. Okay, so we can very easily verify that. So we here we show a formal proof, but we can very easily verify that from here, right? So uh, if you take this half space, if you consider any 2 points, and then the line segment between those 2 points are in the half space, right? So that means this is a convex set. But if this is is this affine? No, because if you take these 2 points, then we have to check the entire line passing through those points lies within this half set. No, right? Because if you consider the line, it is like this. So this part of the line is not within the half space. So that is not affine. Okay. Next, we will see what is a Euclidean ball and an ellipsoid. A Euclidean ball, B ball with center XC and radius R, is defined as the set X such that the Euclidean norm X minus XC is less than or equal to R. Right? What does this mean? This means that you have a center XC, sorry, center XC, right? And then this is like the normal definition, similar to the definition of the circle, right? So then distance from, it is the set of the points where the dist distance from XC is either R or less than R. That means triangular region here, right? So, so this is how we define the board, the Euclidean board. So remember that here the definition is with respect to the Euclidean norm. That's why we write 2 here. So, but this boards, later we see that this board can be defined for any norm. Okay. So Euclidean board is a special category of board. Equivalently, we can define the same board, Euclidean board, using a similar vector notation where this is something similar. You are saying that you are having a center XC, and from there you have a vector RU. Okay, so you magnitude of u can be 1 or less than 1. So based on that you have this board. So this is where u equal to 1, but if you reduce the magnitude of u, you will get some points inside like this. So that again, it's a similar definition. So now we will show that this ball is a convex, but here we will not prove it. But on the next slide, we will prove it using a general definition of ball, not only for Euclidean, for all other balls. We will prove that this is convex. Now, ellipsoid. What is an ellipsoid? So here you can, this quantity you can write as x minus xc transpose x minus xc. Okay, this was this Euclidean norm. Now we saw that Euclidean norm is sort of symmetric, right? It is symmetric. It has same distance in all the direction. But what happens if you want something like this? I have some preferences across different dimensions. I want this radius to be higher and this to be smaller. So then this shape is called ellipsoid. So that set is called ellipsoid. So how do we define ellipsoid? Again, the definition is something similar, but in here we had x minus xc transpose x minus c. Instead of that, we plug in same definition. We plug in a matrix P here, P inverse. Why? Because we have to introduce this difference in length, right? So here you can easily prove that. We are not going to prove that, but we can easily prove that the axis will be lambda 1, and this length will be 1 by lambda 2. So what I'm saying is this length of the semi-axis of the ellipse, that will be 1 by, sorry, 1 by root lambda 2, where lambda 1 and lambda 2 are the eigenvalues of P. Okay, so again, what happens? What you have to do to convert this ellipsoid to a ball? You have to make lambda 1 and lambda 2. So this is in R2. Okay, so we will be having many lambdas based on the dimension. Here we have two lambdas, and so if you make lambda 1 and lambda 2 to be equal, then we have a ball here, right? If both these guys are equal, then we have a ball here. So in that case, the matrix P will be uh, having equal eigenvalues. Equivalently, we can say that that is in the form of a identity matrix. Yeah, so here an important thing is we cannot choose any P. P has to be symmetric positive definite. So what is symmetric positive definite? So this is a very important concept. So there are different classes of matrix. So one very useful class is that you have to learn is symmetric matrix. So the metric matrix is a matrix where we can write A transpose equal to A. The transpose is that matrix itself. Okay. So in that case, so here we are only talking about real. Okay. So the same sort of a similar definition using Hermitian matrix can be done for convex valued matrices, but here our discussion is with respect to real matrix. Yeah, so if you take a transpose of a matrix and if you get the same matrix, then that matrix is symmetric matrix. What is the one of the interesting property of such matrix is that the eigenvalues of that matrix, symmetric matrices are real. So we usually represent Sn. Uh, Use this notation for a symmetric matrix of dimension n cross n. Of course, the matrix has to be square matrix uh, to qualify for a symmetric matrix. Yeah. So now again we learn a subclass of this matrix, which is called a positive definite matrix. Okay. So it is a special class of symmetric matrix where we can write this relation. If you pick any x and take this matrix x transpose Ax, okay, that has to be non-negative. Okay, equivalently you can say that this is equivalent to saying that all eigenvalues of the matrix A is non-negative. So we are not proving this, but we can prove this. Okay, in this course we are not proving this, but you are encouraged to see the proof of this. So if you have a matrix and if all the eigenvalues are either positive or equal to 0, then we can call that matrix as positive semi-definite. So we use Sn plus to denote a positive semi-definite matrix. We also have a positive definite matrix, a different class, which is a subclass of this matrix, which is positive definite matrix. So that is very similar, except from the fact that here the inequality has to be strictly satisfied. Okay, so eigenvalues has to be greater than or equal to 0. With that matrix, positive definite matrix, we have to denote by Sn plus plus 2 plus to denote that it is strictly positive. So here we say that when we define an ellipsoid, this matrix has to be positive, strictly positive definite, right? Why? Because you know that here the length of the axis is 1 by root lambda 1. So this cannot be negative. Lambda cannot be negative or 0. In that case, we cannot define the length of the matrix. So if you want to define an ellipsoid, then P has to be symmetric and positive definite. Okay, now we'll see what is norm boards and norm cones. Okay, so norm board. So we just define what is a Euclidean board, right? So it's a board, at center x having a constant distance r. But how do you here we set previously we set a constant distance. We have a center xe and at a constant distance from xe, right? So, but we can define the same goal using different norms, not only Euclidean goals, Euclidean norm, other norms also. So in general, definition is very simple. A norm ball with center xe and radius r is defined as the norm of x minus xe is less than r. So previously we used for Euclidean ball, we specified which norm it is that, right? Euclidean ball. Euclidean norm. So if you say, if you write 2 here, that means it's a Euclidean ball. Okay, but so if you write, if you consider Euclidean norm, then we know that it's a distance, right? It is the distance from xe, right? So we say that that distance has to be less than or equal to r. But we can come up with different kinds of norm. Norm. This always need not be a distance. So then we introduce a function called norm, a general function norm. So Euclidean norm is a special class of this function, a special norm. Okay, but this norm can be any. There are different kinds of norm. It can be a one norm, two norm, or infinity norm. There are a lot of norms, right? Okay. But in general, a function which is denoted like this, which is associated with a vector space, is called a norm only if it satisfies three conditions. One is that norm has to be non-negative. Okay, so this will be, the norm will be zero only if x equal to zero. And second is this property. This is called homogeneity. Okay, we multiply a vector x with a scalar t, then you can write that as mod of t and the norm of the vector. Okay, then the third property is triangular inequality that we already know. Right, so for example, if you consider a Euclidean norm, it is easy to verify. You are in a ground. For example, you are here and you want to go to this place over here. Okay, so this distance, this vector is x, and this vector is y, and this vector is x plus y. Okay, of course you will choose this path, right? Because it is the shortest distance between these 2 points. You will not go like this, right? You will not take this path. So then we say that the length of x plus y is less than x and y, right? This is a famous triangular inequality. And so here we discuss using Euclidean norm, but this is valid for all norms. Okay, so only you can define a norm only if it satisfy these three properties. Now, so we already defined what is a norm board, right? Using a general norm, right? So here onwards, when you specify a norm, if you simply write like this, it is not clear which norm it is, right? So then this has to be considered as a general norm. If you want to mention a specific norm, for example, Euclidean norm, then you should write to here. Okay. Now let's see. Uh, let's see whether the norm boards are convex or not. Let's check it out. But by yeah, let's see what it is. Let's consider two vectors x1, x2, which belongs to the board, norm board with center xe and radius r. Okay. So what can we say from this, from the definition of norm board? We can say that x1 minus xe is less than r. Also, x2 minus xe is less than r, right? Now, Now, as usual, we will check a new point y, new vector y given by theta x1 plus 1 minus theta x2, whether the for theta belongs to 0, 1, whether this belongs to the, whether y belongs to the same board. Okay. So what? So then for that uh, we have to consider the criteria uh, from the definition of the norm board, right? So we will check this quantity whether y minus xc. We will examine what is this. If that this quantity is less than r, if this is less than r, then we can say that they satisfy. Then we can say that y is in the norm board, right? Yeah. So let's see what this is. This is equal to, now y is equal to theta x1 plus 1 minus theta x2, right, minus xc, right? Now you can rewrite this as theta into x1 minus xc plus 1 minus theta into x2 minus xc. Okay, so you can just practice, do this and verify by yourself. You only, what you have to do is you add theta xc and subtract theta xc and group terms to get this expression. Okay, yeah. So yeah, then we can, now we can apply the inequalities here, some of the inequalities, and continue the derivation. So now we can say that this quantity is less than or equal to. So now we have sum of two terms, right? We split the sum and we write as theta into x1 minus xc. So this is one term plus 1 minus theta into x2 minus xc. Okay, so here which inequality we apply? Triangular inequality, right? Equality. Now there is a scaling here. We can take that scaling outside, right? Here we, so how to take that outside? So here we don't need to put absolute value of theta because we consider theta to be positive in this range 0 and 1. So we can uh, easily write this as, this is less than or equal to, we take theta outside, and x1 minus xc plus 1 minus theta into x2 minus xc, sum of that. So here we applied homogeneity, right? Now this is simple. We know that this quantity is less than or equal to r, and this guy is also less than or equal to r, right? So we can write as, so this is again less than, sorry, less than or equal to r theta, right? So because we know that this is less than r, so we replace this norm with r and use this inequality again, plus 1 minus theta into again r, right? So this is equal to r theta plus r minus r theta, which is equal to r. So we prove that y minus xc is less than or equal to, norm of y minus xc is less than or equal to r again, right? So that means y is part of the board, norm board, and so provided x1 and x2 is part of norm board, then the convex combination of that is again part of the norm. So norm boards are convex. So we made a general proof here. So then any norm, for example, if you take a Euclidean norm here, That also you can set there. That set is also a convex set. So that is about norm board. Yeah, again, one more thing. It is interesting to see different kinds of norms. So we just saw Euclidean norm. There are other kinds of norm also. We'll just go through them quickly. So here I am considering various kinds of norm, and I'm just drawing the unit norm circle in 2D to like visualize how they look like. So here, different norms we are considering. One is Euclidean norm, which we already know, which is defined as like this: the square, sum of the square of each element, and take the square root of that, right? So this we already know. Maybe you already familiarized with the. If you replace 2 with a p here, then just replace all the 2 with p, right? So this is a p norm, okay? And we have one norm here, which is basically sum of all the absolute values. And then there is an interesting norm called infinite norm, which is defined as max of x's. Basically, you take all the elements, magnitude of all the elements of the vector, and consider the maximum of that. So that is also which is denoted as infinite norm. And there is another guy called zero norm, where you just this is equivalently, you can say that number of non-zero elements in the vector. For example, if the vector is something like 1 2 3, then the zero norm is 3 here. But if vector is 0 0 2 5, then in this case zero norm is 2, because it has only 2 non-zero elements. So this is basically non-zero elements. So at home, you can verify that the norm circle. How does the norm circle look like? For example, if you consider a 2 norm, x2 equal to 1, you already know that it is a circle at the center, right? A circle with the center 0, right? And if you take 1 norm, you will get something like this. You can, so basically in R2, you are saying that this is the one norm, right? So you are saying that absolute value of x1 plus x2 equal to 1. So if you consider different cases like x1 is negative, x2 is negative, you will get different equations of line. Then you can draw this, okay? And also you can verify that the infinite norm has this locus. And so this is the one norm. And if you consider a p norm where the value of p is less than 1, then you will get something like this. Okay, so for example, this is a particular p norm locus. Okay, and then if you consider zero norm, then so this will reduce if you decrease the value of p, and at last when p equal to 0, you will get this portion. This is the zero norm. Okay, so this is very useful. You should have an idea of how the unit norm circle look like. But of course, here I was talking about circle. But to get the corresponding bold, you have to consider all the points within that circle, right? For example, a one norm bold, we saw that one norm locus is something like this, right? So if I want to draw a one norm bold with the radius r, that will be all the points inside this. Okay, yeah. So we continue our discussion. Next is norm con. Okay, so this is a special set. Here, how do you define norm con? Norm con, it is this pair. We have x here. For example, x is in Rn. Okay, then another scalar t. Okay, and then you form this couple, this pair xt, such that the norm of x has to be less than t. Okay, of course, when you say no, then that is a positive quantity, right? Here we saw that. So then it is understood that has to be greater than or equal to 0. So how does this norm cone look like? For example, here we are showing a Euclidean norm cone. So what you have to do is take a particular t, for example, t equal to 0.5 here, and then collect all the points. So this height is 0.5. Okay, this is 0.5, and collect all the points which are less than or equal to 0.5. Okay, so here all the x values. So all these values here comes in this circle will be part of that norm. So then you vary different, you vary this, you repeat this for all the for different heights. That means different values of t, then you will get this shape. So what we have shown here is the Euclidean boundary of the, this is the boundary of the Euclidean norm cone in R2. That is this guy. Okay, so the cone, of course, will contain all the points inside this boundary. Okay, and so another interesting factor is that when you form a cone, you are increasing a dimension, right? Xn was in Rn, but this together, this guy is now in, this guy is now in Rn plus 1. Because x was, for example, here x was having dimension 2. Now you increase the dimension by adding a third variable, right? So now this is in R3, right? Okay, and also this is yeah, so we can, this is using a Euclidean norm, but we can form a norm cone with any norm, right? So this definition is general. So for example, if you consider a one norm here, then that will look something like this shape, something like this shape. Okay, you can just draw and verify this. Okay, now is the norm cone a convex set? Let's see. Again, it is easy to prove. So what we are seeing here is, yeah, so what is a norm cone? We know that it is a set. For example, let's call B. Let's denote the set as B, which is the pair X, vector X and T, such that the norm of X is less than or equal to T, right? Yeah, so now let's consider 2 points. Let's assume that X1, T1 is a point, okay, belongs to B, which, yes, belongs to B, and X2, T2 belongs to B, okay. This implies that norm of X1 is less than T1. This implies norm of X2 is less than T2, right? From the definition, from this definition. Okay, now let's call this guy as 1 and this as 2. Now let's take a new point, xt, which is the converse combination of these two guys. So theta x1 t1 plus 1 minus theta x2 t2. Okay, so we assume theta is between, so theta is between 0 and 1 because this is a converse combination, and we want to investigate whether this guy is part of P. Okay, so just expand this, then we'll get theta x1 plus 1 minus theta x2. Okay, plus theta t1 plus 1 minus theta t2. So this is my x, this guy, and this is the t, this guy. Yeah, now only thing is we want to investigate, or we want to see what is the norm of x, right? So continue. Norm of x, which is equal to norm of, what is x here? X is this guy, right? Theta x1 plus 1 minus theta x2. So actually when you write the vector, you have to put a underscore like this. So even if I forget sometimes, this is understood, okay? Sorry for this. Yeah, so theta 1 and theta 2. So we are investigating this quantity. Now, yeah, so what you have to do, you have sum of two terms inside a norm. So then just go for the triangular inequality, theta x1 plus 1 minus theta x2, right? Now this is not equal, this has to be less than equal to. So this is the triangular inequality, right? Again, we can apply the homogeneity, take theta outside, plus 1 minus theta x2, right? This is homogeneity. So now we can see here, right? Here we say the norm of x1 is less than t1, norm of x2 is less than t2. So we can write as this guy here is less than or equal to theta t1 plus 1 minus theta into t2, right? What is this guy? This is equal to t. All right, so we proved that x, which was converse combination of x1 and x2, satisfy this inequality, and hence x is a part of the set B, and hence norm cones are converse. Okay, so next topic is polyhedra. What is a polyhedra? It's a solution set of finitely many linear inequalities and equalities. So we have some inequalities here and equalities here. So we already saw that this sort of inequalities represents uh, a half space, and this is a hyperplane, right? So we can write a polyhedra as set of x. This is a set of x such that ax is less than x is less than or equal to b, and cx is equal to d. Okay, so one important thing here is that we are using a special notation for inequality like this. This means here, this is not a like this is not like when we say 2 is less than or equal to 3, right? Right. So this is different. Here we are comparing two vectors. So this is component wise inequality. So this is a special class of generalized inequality, which we will study later in the following lectures. Okay, but as of now, you just see that uh, when you when you say vector A is less than or equal to b, vector B, that means component base. Each component of vector A is less than each component of vector B. Okay. Now, yeah. So that is the definition of polyhedra. Yeah. So then here is an example where you have different half spaces. For example, this guy. So here you have five different half spaces. So first half space is this one. So then when you say A transpose X is less than B, you will get something like this region. Okay. Then you are saying that, then you consider the next guy over here, and you will say that A2 transpose X is less than B. Then you get something. So this side of the same. Okay. Now, if you take you form half spaces using all the A's, okay, so five A's are there. So you have five different half spaces, and then if you take the intersection, you will get this set here, which is a polyhedron, right? Now you may wonder why you in the definition of polyhedra, why there is a uh, there is a hyperplane, right? You could only define this using half spaces, right? But no, for example, here, let's say you have a box here, which is defined by six different half spaces, okay? Now you have a box, but what happens if the uh, polyhedra that you want is this guy in the black box, okay? This guy. So in that case, you cannot define this polyhedra just by using half spaces. You need a hyperplane also. Then you say that my hyperplane or my polyhedra is the intersection of all these half spaces and this hyperplane. Okay, then you get this guy. So that's a concept. Also, a polyhedra can be a hyperplane. It can be a line. It can be a ray, a line segment. So all these guys are examples of polyhedra. So remember that polyhedra may not be always having this kind of shape. Or we can also think about these guys as a polyhedra. So then we already saw that polyhedra is the intersection of finite number of half spaces, right, and hyperplanes. Yeah. The proof that the polyhedra is a convex set you can verify by yourself. It's very easy. Okay. Next, we saw what is polyhedra. Now, next is positive semi-definite cone. So we already introduced certain notation, uh, which is a symmetric matrix, which is denoted as Sn plus 1. Okay, right? What is a symmetric matrix? It's a matrix where the transpose of the matrix is that matrix itself. And then a positive symmetric matrix, this also we saw, which is a matrix. A matrix is said to be a positive symmetric matrix. Then for all z, if you take this guy, z transpose x z, that should be non-negative. Then the third one is positive definite. Again, the same definition, how strict inequality here. So here, you may notice this a new inequality here, right? So previously we saw that when you compare two vectors, A is less than or equal to B. When you say this, that means this is component wise, right? Now we are saying we are comparing two matrices. X is less than or equal to Y. This is what we are writing. So this is a different inequality, which implies that Y minus X is positive definite. Oh, so here positive semi-definite means Y minus X belongs to Sn plus. Okay, so when you compare two vectors, it is a component wise, and for matrix that is defined using the concept of positive definiteness or positive semi-definiteness. If this is strict inequality, then that is positive definite matrix. Okay. Yeah, now we prove that there are some interesting factors on this. So all these sets are convex set. The set of symmetric matrix is a convex set. Set of positive definite or positive semi-definite matrix is a convex set. How do we prove that? Let's first take a symmetric matrix. So we are taking, actually what we are taking is a set of symmetric matrix, right? So we have, let's take two matrices x1, x2 belonging to Sn, symmetric matrix, right? That means we can write from here, we can write x1 transpose equal to x because that is symmetric, and x2, sorry, x1 transpose equal to x1 and x2 transpose equal to x2, right? Now we take a new matrix y, which is equal to theta x1 plus 1 minus theta x2. Now we see what is y transpose, which is equal to the transpose of this guy, right? The transpose of this guy, which I can write as, you can take transpose inside, then write as x1 transpose plus 1 minus theta into x2 transpose. You know that x1 and x2 are symmetric matrices, right? Which hold this property. So then we can write this as theta x1 plus 1 minus theta x2, which is our original one. Right? So then we prove that y transpose equal to y. So if you take any two matrix in the set of symmetric matrix and take the convex combination, and then the resulting matrix is in y. So here we consider the converse combination theta belong to 0, 1. So symmetric, this guy is a convex set. Next. So one interesting factor here is that we can verify this. This set Sn is a vector space with dimension n into n plus 1 by 2. This means that any matrix, symmetric matrix Sn can be represented as a point in a vector space having dimension n into n plus 1 by 2. How? Because, for example, let's consider a matrix, symmetric matrix x1, x2, x3. Okay. So here we have three elements. Since this is symmetric matrix, this guy has to be x2, right? It has to be same as this guy, x2. Then this is a new element, x4, x5. Now this guy has to be same as x3. So here we have two extra elements, two new elements. Uh, and here this guy has to be x2, and this guy has to be x5, right? x5 and x6. This is a new guy. So here we have one new element. So total number of entries here is 3 plus 2 plus 1, right? So if you go for an Sn, here we went for S3. If you go for Sn, then it will be n plus n minus 1 plus n minus 2 up to 1, which is equal to n into n plus 1 by 2. So here onwards, if you have a symmetric matrix or a positive definite matrix or positive semi-definite matrix, that can be represented as a point in a vector space having n into n plus 1 times. So it can be represented as a point in a vector space having n into n. Here, the vector space is having 3 dimension, but you can consider a vector space with n into n plus 1 by 2, and a point in that represents a symmetric matrix. Yeah, so here we prove that set of symmetric matrices R, that set is a convex set, right? Now, just a second. Yeah. Now, next one is set of positive semi-definite matrix. So we know that that is again convex. We'll prove that, but in addition, that is a convex cone. Okay, so we just prove that this is a convex cone. Then we know that convex cone is already a convex, right? So just let's see the proof. Yeah. So again, here we consider positive semi-definite. Okay, so what is that set? It is set of all matrices X belongs to, of course, that has to be a symmetric matrix, right? Positive, all the positive semi-definite of all the positive definite matrices are symmetric matrix. So that is a matrix such that X is greater than or equal to 0. This means X is a positive definite matrix, right? So if you collect all such matrices, then that set is this one. Now, let's take two guys, x1 belonging to x1 and x2, which belongs to Sn plus. What does this means? We can write that for any z, this quantity z transpose x1 z is greater than or equal to 0, and z transpose x2 z is greater than or equal to 0, right? Now we are going to prove that this is a convex cone. Okay, so now we take the conic combination theta x1 plus theta theta 1 x1 plus theta 2 x2, where theta 1 theta 2 is greater than or equal to 0. This is the conic combination, right? Yeah, so in that case, what is the new guy? Let's see what this is. The is a transpose into theta 1 x1 plus theta 2 x2. Let's see what this is, which is equal to theta 1 into z transpose x1 z plus theta 2 into z transpose x2 z, right? So now we know that this is these two guys are positive or non-negative, right, from this definition. And these guys, we already say that they are non-negative. So this is also non-negative. So altogether, this has to be non-negative. So this is again, this converse combination is again, this belongs to the set Sn plus, Sn plus. Okay. Yeah, so we saw that set of positive semi-definite matrix is a convex bond. So that is again convex. Okay, now for the positive definite matrix set of that matrix, you can also follow a very similar proof. It's very easy to prove. Yeah, so here is an example. So we are considering a set of positive semi-definite matrix in R2. Okay, so we already said that any symmetric matrix, this is symmetric matrix, right? Any symmetric matrix can be defined, can be considered as a point in a vector space having n into n plus 1 by 2 dimension. So here n equal to 2. So that means this is 2 into 3 by 2 is a third dimension, 3 dimension, right? So here we have that. So we have x, y, and z, and so any point uh, in this space represent a matrix here, right? So to draw this diagram, what you have to do is let's like take a point, and then you have all the x, y, and z values. You have x and y, z values. You plug in that values and form a matrix, form a symmetry matrix, and check its eigenvalues. If the eigenvalues are non-negative, then that is part of a cone, right? So that is part of this set, right? So like for example here, if this point does not lies in this set of positive semi-definite matrix, so then that is not the part of that set. So verify this for all the points and collect the points that lies within this definition. That means which is having positive eigenvalues. Then you will get this cone over here. Okay, so this is a convex cone.